Good morning and welcome back to Computational Physics 2, Computational Quantum Mechanics. So I'm going to again use a mix of a Jupyter notebook because I'm going to run some codes and also the whiteboard. And after the lecture, you will obviously find the recording and you will also find the handwritten notes. The ingredients today for the lecture is actually a short repeat of what we did last week, and also a link to the C++ and the Python templates. And these are things which we will discuss during the lab sessions. So the main topic today is actually to go through the derivation of the Metropolis algorithm. So I saw from last time that not everybody was familiar with the Metropolis algorithm. So we will spend some time on Markov chains and the Metropolis algorithm itself. And we are going to derive it in its simplest form, which sometimes is called the brute force Metropolis algorithm, because we are going to let our random walkers just jump around in space following a uniform distribution. Then later, we will modify that, and we are going to introduce something which is called the Metropolis Hastings algorithm, which is a more general case. And then we will discuss a topic which is called importance sampling. This is something we will discuss next week. And that is something which often allows us to select points. In our case, it's going to be coordinate space. We're going to select points in a more meaningful way. Then we are going to look at some basic statistics, and then back to the structure of the variational Monte Carlo code, which we are going to develop. So as I said last time, in the lectures, I'm going to keep a simple Python interface. It's very easy to translate these back to C++. Actually, these codes, which you will see, are originally translated from C++ to Python. And the reason why I do that is that it's mainly pedagogical, because it's easy to run some of the examples during the lectures. And then you can see the basic structure of what you need to implement. Okay, so just some few more messages to remind you of some of the technicalities. So we have a GitHub address for computational physics, which everybody probably has seen. And you can, if you click on the code link here, you can download everything. If you wish to have weekly updates, you can clone it and then just use a git pull and you will get my weekly updates. Alternatively, you can fork it and then use it as your own material. So feel free to use everything here as your own teaching material. And one thing you can do is actually to take my source files and develop them into your own lecture notes. Now, so this is basically where you find the information, everything. And if you go to the doc folder, you will find examples of lecture notes, the handwritten notes. These are the whiteboard notes, actually. And then if you go to the pub folder, what you will find then is the weekly material. And if you then also go to the University of Oslo, so if you go into, so I thought I had that one up here, so I need actually to bring it back again. So if you go to the official website of the university and you click on the spring semester 24, by obvious reasons, then you can find the schedule. And in the schedule, if you click on lectures, you will find after the lecture, the video of the lectures, and you will also find the link to lecture notes. And normally these links are links to Jupyter notebooks, but you can also find everything as a PDF file, or if you prefer HTML format, this is up to you. And there you also find the Zoom link in case you cannot be here in person. And as you know, probably, so this is just a boring repeat of some of the messages in case you missed them. You can subscribe to these activities so that you can get a message when things change. We use also Canvas, and there are also upload much of the same information. And I guess everybody now is receiving the weekly mails, right? Is somebody who doesn't receive them? Okay, excellent. So that should give you roughly the kind of overview of what we plan to do. Now, during the lectures, we will discuss a little bit more about the basics. So this is the first thing, is a repetition from last week. And then I want to link to you the C++ template in case you want to write everything in C++, which many plan to do. But there is a similar template in Python, which uses JAX, which allows you to vectorize and parallelize Python codes. And it also includes the automatic differentiation project. So automatic differentiation is something which is extremely useful when you're going to calculate derivatives. So we will come back to automatic differentiation a little bit later. But if we now, unless any questions about practicalities, I wanted to say something about what we did last week. And where we did start was actually with the expectation value of the energy in terms of a wave function, which is not necessarily the eigen function of the Hamiltonian H. So if we had the eigen function, I mean, essentially then we have solved the problem. And there is no need for me being here. And there's no need for you guys being here, because we've just solved the problem. But what we are going to do now is actually to bake in different ansatses for the trial wave function. And the variational Monte Carlo method is based on us evaluating this integral using stochastic integration, because this integral is normally a high-dimensional integral. And these multidimensional integrals, they are normally evaluated with Monte Carlo methods. That means stochastic methods. And these are the things which we will be discussing and implementing throughout the semester. And as we mentioned last time, one of the reasons why we deal with Monte Carlo methods is that they have a, what we might call a lower mathematical entry point. So many of the typical many-body methods, like some of you who have taken a course in many-body physics know, they are pretty convoluted with lots of mathematical formulas. So Monte Carlo methods are much more intuitive and much more straightforward to implement. So essentially what we end up doing is to evaluate a multi-dimensional integral with stochastic methods. And then these functions which we have here, these are normally guesses on the trial wave function. And that contains often our physics insights, or for those of you who want to try neural networks in project 2, that's a continuation of project 1, we can then replace the trial wave function with a neural network. And this has been extremely successful in the last years in the solution of many-body problems. The variational principle, which many of you have encountered in quantum mechanics, is the basics. And you can see a quick reminder here of the variational principle, which simply says that the trial wave function we have, unless we have the exact one, will give us an energy which is larger than the exact energy for that specific Hamiltonian. So often what people may do is that they try different trial wave functions, and then clearly they would pick the one which gives the lowest energy. As we also discussed last time, even though if we don't know what the lowest energy is, we know that the variance, which is a statistical quantity, which is the expectation value of the energy squared, minus the mean value or the expectation value of the energy squared, that one is exactly 0 in case we have the exact wave function. So what people often do is that they try different ansatses for the wave function, and then they look at the variance. So obviously you will want lower energies, and you also want a variance which is close to 0. And then if you are to select between, let's say, 2 trial wave functions, you would pick the one which gives you the lowest variance and the lowest energy. So the variational principle, as we discussed last time, plays an important role. And what we wanted to do in order to be able to do statistics, and we are coming back to this, is actually to rewrite the integral you see here as a statistical expectation value. And the trick is to redefine the integral in terms of, one, the probability distribution. So this is the quantum mechanical distribution. And one of the things you will see today when we discuss the Metropolis algorithm is that this quantity, which is given by the probability distribution, depends on a normalization factor. And this normalization factor is as difficult to calculate as the expectation value of the energy, because we have because we have to evaluate a multidimensional integral. When we deal with the Metropolis algorithm, what happens then is, one, we are taking ratios between probabilities. And then the normalization factor, which is the nasty piece in these calculations, disappears in a ratio between probabilities. So that's one important thing. The other important thing is that when we perform a Monte Carlo calculation, what we are doing now is to rewrite this integral in terms of a quantity which we call the local energy. And this is the quantity which we will calculate the expectation value of. So we are actually, and this is the same, it results in the expectation value of the energy. So we will have a probability distribution multiplied with this quantity. And the second thing, when we do a Monte Carlo calculation, when we evaluate it stochastically, is that we are going to pick positions or configurations, if you prefer that. So this R is a container for all the positions of the particles. So if you have 10 particles in 3 dimensions, this is a 30-dimensional object. So that would be X, Y, and Z for particle 1, X, Y, and Z for particle 2, etc., etc. And these are selected randomly. And we need to find a rule in order to accept these random selections. And the rule is given by the Metropolis algorithm. So what we in practice end up doing, which also avoids the calculation of the normalization factor, is this sampling over all the possible distributions which the particles can take. So that means that the normalization factor which we had here in our practical evaluations disappears here. And then it's common to invoke the Bernoulli's law of large numbers, which simply states that this quantity here now approaches the true expectation value in the limit of infinitely many samples. So these are the essential elements. And one of the things which we did last time was to sketch the algorithm and show some implementation, some simple ones. And today, at the end of the lecture, we are going to look at how we can do this for 2 electrons which interact. And this is going to be pretty similar to the system which you will have in the project, in project 1. So the basic Monte Carlo algorithm, the simplest one. So this is the Monte Carlo algorithm, everything you see here. And you would then initialize, fixing the number of Monte Carlo cycles you want to do. I'm going to use Monte Carlo steps or cycles interchangeably. You choose an initial position and an initial wave function with some parameters alpha. And then you calculate a new trial position, and then you suggest a move to this new position, and you calculate the ratio between the probability. This is the Metropolis algorithm, which sits inside the Monte Carlo algorithm. So the Metropolis algorithm is the rule which you use to accept a suggested move. And when you do that, you can, by obvious reasons, you can stay in the same place if you don't accept the move. That is also an observation, or you move to a new position. And today, we're actually going to derive the Metropolis algorithm so that you get a feeling. I know that not everybody has seen it. So for those of you who have seen the derivation, this may be a little bit boring, but I hope you can survive. And then you update the averages, and you finish and compute the final averages. This is the essence of what you're going to program. And here, last week, we had an example of a harmonic oscillator in 1 dimension, and then the trial wave function for the ground state. And since we are going to look at bosons, we can actually place all the particles in the lowest lying single particle state. And this is a 1 particle in the lowest lying harmonic oscillator state. And here we put the what's normally called atomic units, sometimes natural units. So we are scaling away the physical constants. It's always boring to bring them back because it's easy to make errors when we want the right dimensionalities and units. And then we put omega, the frequency, to 1, the oscillator frequency, and this is the trial wave function where it's alpha as a parameter. We can then, and this was one of the exercises we had last week, you can then calculate the local energy. So this means the local energy is this quantity which you see here when you take that trial wave function. And then that expression is an expression which you can integrate analytically. And this is what you should get. This is the expectation value of the energy as a function of these parameters alpha. You can also calculate the analytical expression of the variance. Oh, by the way, this should be E squared. Sorry, that's a typo. I didn't see that before now. So this is an E squared here because that's the expectation value squared. This is the expectation value of the energy squared. And everything can be calculated analytically because your local energy is this quantity. And when you go back then, when you want the energy squared, then you simply need to square that local energy. And then you have the probability here, which is given by the wave function squared. And your wave function is this one. So it's an integral with Gaussians. And this is something you can easily look up in mathematical formula, or you can invoke symbolic Python or Mathematica, and it can find the integrals for you. But these are the analytical expressions, and you can compare them to your codes. So the first code here is actually, I think we went through that last time, but I could just rerun it. So this is just some initializations. And now I'm setting up the analytical expression for the wave function and the analytical expression for the local energy. And then I perform my Monte Carlo calculations. I am doing 100,000 Monte Carlo cycles. I have a step size, all positions. I run over a series of these parameters. I know that at 1, I have the exact result. And then I'm performing the Metropolis test here, which we will discuss a little bit more in detail today. But I'm just going to rerun this because this is something which we did last week. And I had 20 parameters alpha. And then we saw that when we had 100,000 results and we went to alpha equal to 1, that's when we have the exact result. And with these units in 1 dimension, the energy is 1/2. And if you go into a textbook of the harmonic oscillator, this is the 1/2 factor. And then if you have a different frequency, you need to multiply that with h bar times omega. But this is then the exact energy. And you see also then that the variance is exactly equal to 0. Now, the theoretical one and the computational one, they differ when we have moved away from the minimum. You see that there's a minimum here. And this is the basic principle of the variational calculus. So we are essentially going to optimize to find the minima of a function which is convex. So the energy is always the minimum. And in general, the Hamiltonian leads to a convex optimization problem. So what we are going to do now is actually to look at Markov chains, because we need to discuss a little bit more the theory for the Metropolis sampling and the Markov chain machinery. So if you now look at the words here, I just wanted to bring them up because if you go back to the expression which you have here for the probability distribution, even if you have an analytical expression, in general, this is a nasty animal to evaluate. So just think of that expression for 10 particles in 3 dimensions. It means that this object which you see here, this psi of t, is a 30-dimensional object. So it means that if you want a value for the probability, you need to plug in 30 input values. So that tells you that even if you have a nice analytical expression, this is a complicated and computational expensive object to use. Okay? So when you are going now to look at the different calculations we are going to run, you will see that in the Metropolis algorithm, we can often reduce that complexity to just evaluating one particle at a time. So just keep that in mind that what we have in principle is a multidimensional object, which is difficult to evaluate. computationally or expensive. They can be difficult and expensive or just expensive. So if you now go back to the basics here, so we want now to study a system which evolves towards an equilibrium and with some given initial conditions. What we will have is a model for the initial probability. So this can be the Boltzmann distribution, or in our case, it is the wave function square. So it means that we are going to have a model for the probability. So in the lectures here, I'm going to use W as a function for the probability or the state of the system. Then, as I said, this is normally a multidimensional animal. Analytical calculations are often difficult or even not possible. To sample directly is difficult, or sometimes it's even impossible. And then there is a transition probability, because we are going to set up a Markov chain. So a Markov chain has a simple mathematical expression. And the way we are going to simulate these things is by assuming that we don't know this W, which is a transition probability, but that we have a model for the probability of the system. And the probability of the system is our trial wave function squared. That's the model which we make for the probability distribution. So a Markov chain is something which is then based on, and then I'm going to bring up the whiteboard. So let's do that, so we can slow down the pace a little bit. So the basics of a Markov chain. Suppose now that we have this probability distribution. So we have a PDF. The PDF stands for probability distribution function. And we just label this as a W, and this depends on some X and time. So in our case, this is actually the wave function squared. It's time independent. This is the quantity which we are going to study. But let's just, for simplicity, put it like this. Now, suppose now we look at this at a given time t0. So we have an initial PDF. Which we just call X at time 0. Now, what we are going to do then is now to replace this one with just time. So we are going to discretize the position X with just a subscript I. So we're going to rewrite this one as a WI, where this I could be a position. So as an example, you could think of this along a one-dimensional grid. So think of this as a one-dimensional system. And then you have different positions here. And then you have an I plus 1, an I minus 1, I plus 2, I plus 3, etc. So this would be a typical example, and that means that this Wi at a given time t represents the probability of being in this position here at a given time t. Now, a Markov chain is represented by a physical process where you jump from one position to another one with a transition probability. So the mathematics of a Markov chain, or the mathematical expression, is given by a system where we don't keep track of what happened in the step before. So in the Markov chain, we have a mathematical expression for the probability at the time t plus 1, or we can write this as a Wi over t plus epsilon. So we make a small time step, and that is given by a sum over all the previous positions which we had, or all the possible positions, And there's a matrix here. We're going to rewrite this as in terms of matrices and vectors. So think of Wi as a vector. It now represents all the possible position in this one-dimensional system, which you can reach with this probability. And this is given by a transition probability multiplied with u being in a state t, a state j at the time t. So that if you go back to that simple picture which we have here, it means that we may be in a state j here, and we are asking what is the possibility of jumping into a state I in the next time step. So the quantity which you see here is normally called a transition probability, or transition likelihood. Now, you can have a simple model. So if you're thinking of a random walker, you could have a simple expression for that. So that means that you know both Wj, the specific probability distribution, and the probability of making a jump. So a simple Wij is given by the following expression. So we could have this one equal to 1/2. So that means that there's a probability of 50% of jumping left or right. So if I minus j is equal to 1, only in that case, and 0 else. So this is just an example of a very simple probability. So if you go back to what you have here, so what you're saying now is that there is an equal probability of jumping left and right. Actually, people have used this simple model to explain how people vote. And they try to mimic the way people voted in the EU Parliament in Strasbourg. You can obviously question the extrapolation of these mathematical concepts to real humans. And what they found was that in the EU Parliament, it was roughly a 50-50% distribution between left and right, whatever that means. Okay, so what you have then, this is just a simple example where you know the probability. The general situation, which is our case, the general case, we have no idea of what Wij is. So we don't know. So Wij is going to be a matrix in this representation. In principle, if you think of all positions which you can reach, this should be a infinitely dimensional matrix because you have an infinity of positions. But we will always limit the number of positions in our actual calculation. Now, when you look at this statement, which I say here, because even if you were to calculate this one, if you look at, let's say, a hydrogen atom, which is in an excited state, a pre-S state, and then decays to the ground state, in that case, we have a nice mathematical expression for an electromagnetic transition, if that is a transition which takes place. Then this object here would represent the transition probability for an electromagnetic transition from an excited state of hydrogen to the ground state. Now, I don't know if you have taken a course in electrodynamics or quantum electrodynamics, then you've probably seen the mathematical expression for this. This mathematical expression is actually quite involved. If you go to many particles, this becomes way too involved, even if you can calculate it. So you may now ask yourself, if I don't know this expression, how can I actually perform any calculations at all? This is where the Metropolis algorithm comes to our rescue. So the Metropolis algorithm allows us to make an estimate for this transition probability. But we need a model for the probability here. This is the basic assumption which we're dealing with. And in our case, this model is the wave function squared. And then we are going to use the Metropolis algorithm to, in a way, mimic what this actually represents. So you can think of this as a multidimensional set of transition probabilities. And then we need to find a way to model this. Now, if you look at what we have, since we have been talking about probabilities, this Wij, these are the matrix elements of a stochastic matrix. So when we're dealing with a Markov chain, we have a probability Wi, and then since this is a transition probability, so this matrix, this W, this leads to a stochastic matrix, so which is a stochastic matrix. Now, what we have, since we're dealing with probabilities, is that this quantity, which we label Wi, and now I'm skipping time here, but there could be time. This is always now assumed to be normalized. So that means that this is less or equal to 1. This means that if I sum over all i's from 0 to, in principle, to infinity, in principle, and I do this at a specific time t, this should be equal to 1. So this is a basic assumption which we are doing. The next thing which we will do is to make an assumption about these matrix elements. So these matrix elements are actually set up so that they're also less than equal than 1. Now the matrix W is now so that if I sum over the columns, you can choose whether you sum over the columns or the rows. So we are just going to sum over the columns. So if you make a sum over the column elements, this is normalized to 1. So have you encountered stochastic matrices before? Somebody has that? These matrices have a specific property. What is the largest eigenvalue of a stochastic matrix? This is something we will use for the Markov chain process. That's 1. So that means that the eigenvalues, so the lambda of this matrix Wij, the absolute value of it is smaller or equal than 1. So the largest eigenvalue is equal to 1. Say it again? Yeah, that's right. So there is, hopefully, there's only one eigenvalue which is equal to 1. We don't want to have degeneracies, because this becomes important when we are looking at the evolvement towards the stationary state. So I'm coming back to this now with some simple examples. So if you now look at what we have, in essence, we have the following. So we have a Wi, and then we can say at a t plus epsilon. And I'm just going to let this one go. Now I'm going to start at t equal to 0. So this is just a Wi at epsilon. And it's pretty common, if you go into textbooks, to just see this written as a W and then a J going to I, just to indicate that this is the probability of jumping from a position J to position I. So this was our original matrix element, Wij. But I'm going to use this notation just to indicate that there is a process which has a probability of making a transition. And this is now multiplied with this initial state at time equals 0. So we could now think, so what we're going to, a very simple case you could think of is now you coming in the morning, you grab a cup of coffee, and you put a drop of milk in your coffee, right? And you know that at time t equals 0, this milk molecules will be concentrated in a small region. And after some time, you get something which looks like coffee with milk, right? Because then the milk molecules, they distribute themselves in the cup and they reach an equilibrium situation. And the coffee changes color to some latte-like thing, right? And this is the way you could think of it. So you could think of this as your milk distribution, which is then something close to a delta function at t equals 0. And then there are complicated reactions and transitions, which now make the milk molecule diffuse in the coffee liquid. And then you reach this kind of equilibrium situation. That's one, I would say, pretty stupid example for what this represents. There is something which I will not show you, but you can derive the diffusion equations from a Markov chain. So there are some technicalities which I will not discuss, but which are very interesting by themselves. So the process of Markov chains is intimately linked with the physical process of diffusion. So you can derive the standard diffusion equation from actually this Markov chain. So you will see that if you go into my textbook on computational physics, there is actually a chapter 12.2 where I derive the diffusion equation starting with a Markov chain. So this is something which I'm mentioning because diffusion and Markov chains are intimately linked. Now, what if we now look at this specific process which we have, what you could think of now is to repeat this many times. So we are going to make a new assumption. This assumption doesn't need to be true, but we are just going to do that now because it simplifies the mathematics. So we are going to assume that this WT, the matrix, I hope you can see the difference between the lowercase and the uppercase letter, is time independent. In a way, what you could think of is that these jumps are instantaneous processes. You can add time to it, and this leads to the complexity of the Green's function theories, which some of you may have encountered. But now we are simply going to make assumption that these are instantaneous processes and that W is time independent. But there is a time dependence in W, the little one, the probability distribution which we start with. This is the one which is going to change as we perform the simulations. So you could now think of applying this omega, the transition probability, many times. So you could now look at the process where you now have, so we have this Wi of epsilon, and this was given by the matrix Wj to I multiplied with Wj at time t equals 0. So we can write this in a more compact form as a vector times a matrix. So if I is now just one of the positions you can have, and we can rewrite this as a vector of epsilon, and we can write this in a more compact way as a matrix vector multiplication. So we would have a W multiplied with this W of 0. So this is time epsilon. Now we can repeat this process because we assume that this is time independent, the instantaneous operations here. So we could have now a 2 epsilon, and that is simply given by W squared acting on that state. Does that sound reasonable? So we can now do this many times, and we can now have, after n times, n epsilon, we would then have simply this matrix acting n times on an initial state 0. Now, what we are interested in is a state which is stationary. Stationary is going to mean the same as the most likely state of the system. And hopefully, there is only one. If we have degeneracies, then we are going to run into problems, because then the system may oscillate between different many solutions. So what we are going to look at now is how these equations evolve when we move towards the most likely state, or the stationary state. So let's now look at so this n represents time for us. So let's now assume that this W, which is a matrix, and we are assuming it's a finite dimensional, in principle it's infinitely dimensional. Let us assume that this has eigenvectors, has eigenpairs. So with eigenvalues, lambda I, and eigenvectors V of I. So we know that this is a stochastic matrix, and the largest eigenvalue, as you will see in an example of a stochastic matrix, is 1. That's the largest eigenvalue. So let's assume that. Now, that means that we have a basis. And what I could do now is to take this W0 and expand that in the basis of the eigenvectors of the matrix W. So this is a complete basis. We can orthogonalize the basis because we have diagonalized W. So we're assuming that W is a square matrix and it has defined eigenvalues. And we produce now an orthogonal basis. And this is given by a sum over I of alpha I, which is a mixed coefficient of overlap between W0 and V of I. That sound reasonable? I guess you've seen this kind of definitions before, right? You have an orthogonal basis, and then you can use that one to expand a new function in terms of that. So this means the following. When I act with this one on the initial state, that is the same as I acting of W acting on V of I. And this has obviously to be equal to I alpha I of lambda I of V of I. Okay, that sound reasonable? Now I can do this many times. So when I do this many times, this is my final state, W of n times epsilon. And we see that this one is nothing but the sum of I, alpha I, lambda I to the power of n multiplied with V of I. So what happens here? Now comes the interesting thing with a stochastic matrix. So since we have a stochastic matrix, we know that the eigenvalues, so I'm going to order the eigenvalues. So the largest eigenvalue is this one, and this is 1. And this is larger than lambda 1, larger than lambda 2, and all the way up to the final dimensionality which we have. In principle, this n should be infinite. I should put an n here because that's different from the n which I have. So that means that I can now rewrite this vector at n epsilon. I can rewrite that one in terms of the different eigenvalues, obviously. So I have a sum of I, alpha y, lambda y to the power of n multiplied with these vectors. I'm going to define a quantity which is going to be called the damping time. So I'm going to just introduce a variable which I call for tau of I, which is -1, and this can be log 2, it can be the normal logarithm. That just gives a scaling factor, which is void of interest, whether we have log 2, log 10, etc. That's just a scaling factor. So let's just put log. So that means I can rewrite the quantity which I have here, which now becomes equal to a sum of I from 0 and in principle to infinity. And then what I would get then is multiplied with V of I, and then I have an E of minus T divided by tau of I, like that. No, not n, like that. And then we can replace this n times epsilon with time. So I'm just going to replace n times epsilon is my time. So I'm going to take t, which is now equal to I equals 0 to infinity of alpha y v of I, e minus this time is a kind of artificial time. And now you see a very interesting property that this becomes now equal to alpha 0 times v0. And then I know that if I look at the first eigenvalue, the largest one is 1, right? And I take the exponential of that quantity, so I'm just going to get alpha 0 times the v of 0 plus the other terms, I equal to 1 in principle infinity, and I have a v of I of E minus T divided by tau of I. What is important now is that the ratio between, if these states are large, if these states are close to 1, then these terms will be important in the convergence of this process as we move to larger and larger times. But what you're seeing now, if I take the limit of this expression of t goes to infinity, of this w of t, what this converges to is this alpha 0 times v of 0. So this is the stationary state. So my process, this Markov chain, if it reaches an equilibrium, if the transition probability is so that we reach this state, we normally call this the stationary state. Or the most likely state. Let me just put that one, most likely. So that means that at Wt, when we have the limit of t goes to infinity, what we're having then is that we reach a state which is time independent. So this is my probability. So the probability is time independent. It does not depend on time anymore because this quantity which I have here is time independent. These are the eigenvalues, no, the eigenvectors of a matrix W, which is time independent. So this quantity which you get here is normally called the most likely state if these eigenvalues are well separated and we converge towards that. So after the break, I'm going to show you a simple example which you will find in a Jupyter notebook where we will actually see this. And the convergence of it will depend on the values of the eigenvalues. So when we are done with that, we are going to derive the Metropolis algorithm after the break. And then we're going to implement it in a Monte Carlo calculation and show you how we can actually implement it. But the basics for this development towards equilibrium is now given by the Markov chain equations, which as you evolve through time, assuming that this W has well-defined eigenvalues and we don't have degeneracies, then that will evolve towards the most likely state. And that's the state we want to hit when we are simulating. This can be the most likely state at a given temperature, or it can be the most likely state for a quantum mechanical system. So when you run your Monte Carlo sampling, you are essentially implementing a Markov chain. So this is normally called Markov chain Monte Carlo, or just MC squared. This is what we end up doing, a Markov chain, which we let simulate long enough so that you reach the most likely state. And the mathematics is actually given by these equations which you see here. So if you have understood this kind of overarching or this bird's eye view on the equations which we are going to implement, then the essence is actually given in this evolution of a given probability distribution towards the most likely state.
Nei, Morten, jeg tror det er unmuta på kassen din. Morten, kan du unmute deg selv?
I had muted myself actually. Sorry for that. Okay, now you should be able to hear me. Sorry for this. Okay, I forgot to unmute myself. So some of the beginning here will actually be lost as in the recording. Anyway, so what you're seeing here is actually a slow convergence to roughly the 4/5 digit. And what it tells us is that when we run a Monte Carlo calculation, we need to have something which we need to have some Monte Carlo cycles which we simply waste away. It's called burn in time, so that we reach what would normally be called the most likely state. So you could say now that if you are willing to accept a small fluctuation at the 4/5 digit after the decimal point, then you could say that after 50 iterations here, we have roughly reached something which looks like the most likely state. And the rest can be treated as fluctuations around that mean value. So just a small exercise, if you want to, you could take that code, and when you compare the eigenvalues with what you get here, you will not get the same eigenvalue simply because an eigenvalue solver like this one, when we use that lin-eig, doesn't normalize the eigenvectors. So you would need to normalize the eigenvectors if you want to compare what you get from the iterative procedure here with what the eigenvalue solver gives you. So if you then go and look at the lowest line or the eigenvalue with 1, the first eigenvalue, and you pick that eigenvector, you need to normalize that eigenvector in order to compare it with what you see here. And then the numbers should match. So feel free to do that as an exercise. So this is essentially the kind of analysis which we did. And now what I wanted to do, since we don't know this probability, this transition probability, we are now going to introduce the Metropolis algorithm so that we can actually sample in a meaningful way. So let me switch back to the whiteboard. And now what we are going to look at is actually the Metropolis algorithm. So the problem we are facing is that we don't know this quantity, which we label as a transition probability. And you may then ask yourself, how can I actually run simulations if I don't know this equation? Because a Markov chain is actually based on knowledge of that equation. Let's see now how we can change things a little bit. So we don't know W, then we are free to make a model of W. So what we are going to do now is to assume that we have make a model. And that model is going now to be given by 2 types of probabilities. So one, which is the probability of making a transition, which I call for T, and it's normally called a transition probability, even if we call this the transition probability. But what this is going to be, this quantity here, is the probability of making a transition. But what we are going to say now is that even if you can make a transition, this transition may not happen. So probability to make a transition so there is a given probability, and then we are going to have something which we will call an acceptance probability. So you have a probability for jumping, and then this is multiplied with a probability for accepting the jump, so that you end up in the new position. So this is simply just a model which you're making, which was suggested by Metropolis et al. Back in the 40s, in order to be able to simulate the system which we have here. So this is the probability of accepting the move, of acceptance. Now, the standard Metropolis algorithm deals with us estimating this acceptance probability, because that's what is going to tell us if we accept a proposed move or reject it. So how can we find an expression for this? So suppose now that we go back to the Markov chain equation. So if we look back at the Markov chain equation, and we do this after a given number of steps, so we have this n, so we have performed n steps. Now, what we did was to write this as a j, and then we had this transition probability, which we assume to be time independent. And this was multiplied with a wj of n minus 1. This was the original equation for the Markov chain, which is an equation or a sequence which does not depend on the previous values. It just depends on the value which you were at now, and then it gives you the likelihood for jumping to a new state. So we're going to introduce a kind of technicality. So we are going to accept. So let me just define these. So we are going to accept suppose now we look at the state, we are moving to a state J. So we are going to accept that with a probability and I just write this as an A of I to J. If I move from J to I, it's the opposite, okay? Then what I'm also going to use is, so this is the probability of moving to a new stage, but then I can say that the probability of rejecting it is now simply A1 minus A of I going to J, okay? So there are just two probabilities, reject or accept. And the two, if you sum them up, they sum up to 1. Does that sound reasonable? So I'm going to use this to rewrite this equation here. And I'm going to rewrite it as, so I have a Wi of n, which is now going to be given by this sum over j. And now I'm detailing this in terms of the probability of making a transition multiplied with the acceptance. So I am at a stage n minus 1. And now I have a t of j goes to I. And then I have a of j goes to I. So this is as before. But now I want to, so this is a manipulation which I'm doing. I now want to add the probability of actually staying in the same position. So what I do then is I include wi of n minus 1. And this has a probability of t of I going to j. But since I am actually refusing this, then I take a, the 1 of minus a of I goes to j. So I'm just introducing another way of saying that I also want to test whether I can jump from I to j, but then I plug in the probability of refusing that step. So what I'm doing now is to rewrite this equation here in a slightly modified form where I have this term, but then I add something which in principle should give us 0. Now, what is interesting for us now is the following. The thing which I know is that these probabilities are normalized. So when you look at this equation here, there is a sum here over j, but this wi doesn't depend on j. And then I also know that I have a term here which multiplies with 1. So since this sums over j now, that means that this has to be something which is now normalized properly. So that means that if I look back at the definitions of these probabilities, then I have a term here where I'm summing over j, but where I have wi of n minus, not that way, of n minus 1 multiplied with this t of I going to j, and then I'm going to use the orthogonality properties of it. So that means that this is just a constant, this term which you see here, so I can put it out. And this one sums to 1 due to the normalization condition. So this is just going to be equal to wi of n minus 1. Then I can rewrite everything in the following way. So I have a wi of n minus wi of n equal wi of n minus 1 plus, and then I have a sum over j, and I have my wj of n minus 1 multiplied with this t of j goes to I, a of j goes to I, and this has a minus sign of wi of n minus 1, and then this is multiplied with a t of I goes to j, multiplied with an a of I goes to j. Then what we've said is that in the limit when n goes to infinity, these distributions become time independent. So Wi of n, this just becomes equal to Wi. So this is our stationary state, or the most likely state. Stationary. Okay. If I do that, what you will see then is that clearly this equation here cancels that one. And then I have a condition. So what that leads to is simply now that I have a sum over j, and I'm going to make things a little bit easier. So I'm going to say that this Wi, now let's just keep this Wi. So we're just now in replacing the probability at a given time n with a time-independent probability. So we are going to have an equation here where we have Wi, so Wj multiplied with Tj goes to I of A, j goes to I, which is equal to a sum over j of Wi of T of I goes to j multiplied with A of I goes to j. Now, this is a condition which is more difficult to fulfill. And what is normally done, and we can actually show that this is the case, that this actually fulfills the equation for a Markov chain. This is called detailed balance. And the stronger condition is this one, where I have a T of j goes to I, of A of j goes to I, divided by, not divided, is equal to Wi of T of I goes to j, of A of I goes to j. So in the lecture notes, you will find links to proofs of the detailed balance. Mathematically, what you can show is that this condition here is stronger than the previous one, and it avoids what are called circular state. That means that you can, after some time, you can end up in one specific state, and then after some new time, you can end up in another state. It actually guarantees that you will reach the most likely state, obviously depending on the transition probability. Now, what you see now gives us a ratio. So if I now divide here, what I have is that Wi, Wj is going to be equal to the following equation. So that's going to be equal to A of j goes to I, multiplied with T of j goes to I, divided by A of I goes to j, and T of I goes to j. So what we can frame in here is that this equation here, this ratio is known. Obviously, what is on the left-hand side, on the right-hand side, is just given by the ratio. So we don't know what the terms are, okay? So we have a model for the probabilities. So we have a model for, and in our case, this model is the wave function. So note as well, this is an important thing to note, is that the normalization factor of a probability disappears. So the normalization factor cancel. Just keep in mind that our probability Wi is actually given by the wave function, the trial wave function, in a position R of I, and as a function of these different parameters which we have. So these are vectors squared divided by an integral over d over r. And r are multidimensional variables. So what you see now, when you take the ratio, the normalization factor, which is a complication in everything we do, disappears in the ratio. So that is a very, how to say, welcome feature. We don't need to deal with the normalization constant, which is in itself a multidimensional integral. Okay, so what you are going to see now is the following, and you will see why we did split this into a transition probability and an acceptance probability. Because what we are going to do now is to plug in physics in here, and this quantity is just going to be us accepting or rejecting a proposed move. So let's now go back and manipulate this equation a little bit. So what we have is a ratio between transition probabilities, and that is the probability of going from j to I divided by a of I goes to j, so going back again, and that is going to be equal to wi, which is known, wj, and this is t of I goes to j, of t of j goes to I. So this is where we would bake in physics for the specific signs which we are looking after. So this would normally be specific for the case, the given physics case. The simplest thing to do is actually to assume that there is a reversal symmetry. That takes away this physics-based term. So you will see that later when we look at the importance sampling, this is going to allow us to guide the way the random walkers jump in space. Then we are going to make a model for this t. So this t is something we can model to a certain extent, but in general, this is difficult. This is the more difficult part of this transition probability, the total one. So we could assume now, for simplicity, that there is some kind of reversal symmetry. So let's assume that for simplicity. And this will lead to what is normally called the standard Metropolis algorithm. When we include this transition probability, we normally refer to that as the Metropolis-Hastings algorithm. So this is normally something which leads to then A of j to I, and then A of I to j is equal to wi divided by wj here. Okay? And this is going to lead to the Metropolis, just a standard Metropolis algorithm. If I add t, that leads to the discussion of importance sampling, which we will discuss next week. And then we will have what is normally called the Metropolis-Hastings algorithm. Okay? So the thing which is of interest for us now is actually to evaluate this acceptance ratio. And that will tell us whether we will accept a move or not. Now, as you see it here, the only thing you can calculate is just this ratio. If you assume this symmetry, then we have this simpler case here, but we still need to find a way to simulate the values for A. So let's see how it was done in the Metropolis algorithm. The strength of the Metropolis algorithm is its amazing simplicity. So if you make something simple which works, this Metropolis algorithms obeys detailed balance, and it also obeys the ergodic hypothesis. You can actually show that. So let's look at the way you can simulate here. And I will try to develop your intuition here by just looking at the probability. Suppose now that the probability we are looking at is just a plain Gaussian. And it looks like this. So we have a probability Wx, which is this function. And suppose now that you place yourself randomly in this position here, J or Wj. Suppose your Wj here is equal to this function here. So you're placing yourself here. Now you make a suggested move. So suppose now that you suggest that your move goes to a position xi. So this is xj. So this is your probability Wj, and this is your probability Wi, which then is the same as Wx of I. So what would you say about this ratio now? Equal to 1, larger than 1, or smaller than 1? 3 choices. It's greater than 1, okay? So what we have now is a situation where we have Wx of I of Wx of j larger than 1. Is that a move you would advise me to do? So what do you think I should do? Should I move to higher probabilities or should I move to lower probabilities? What would you prefer? So if you replace this with a Boltzmann distribution, higher probability means lower energy. So for the Boltzmann distribution, this has a direct link with the energy minimization principle. So higher probability with a Boltzmann distribution means lower energy. So we want to accept going to higher energy, higher probabilities. So normally we want to maximize the probability. We are not interested in a description of a system where we have the lowest possible probability, right? So when we are describing something, we want to have the most likely state, which is the one which has the biggest probability for that specific setting. So it means that we would accept moves to higher probability. What happens if I only accept moves to higher probability? So as Daniel said, if you now accept only moves to higher probability, you end up here. And you don't move away. So you could happen now that after 10 moves, you're here. And then if you now think of the integral you want to calculate, you would just sample this point here. So suppose you do 1 million samples, 1 million, and you have 10 moves, which bring you here. That means that the rest of the points you will sample are just these ones. And that wouldn't give you a very good value for the integral, right? So we need to also have the case where, so let's bring this up, where xi Wxj is equal to 1. That means you stay in the same place. And we need also Wxi of xj smaller than 1. Okay? So these are the 3 cases. Because if we have that one, the last one, it means that we will move to places where we have lower probability. And that means that we will sample the whole function which we want to integrate. So if we want to integrate this one, we obviously want to avoid a situation where we're just stuck in one place. Also, if we jump with very small steps, then if we start here, we may perhaps just move around here after a given number of steps. So tuning the step which we jump with becomes also important. And that leads to important sampling, which we will discuss next week. But if you now look at what we have here, this is something which we can calculate because we have an expression for the probability. But it doesn't help us in finding a value for that, right? But now I want to give you a hint. So what we are saying now is we have the following, and these are the cases which means that we would accept flatly the suggested move. Either we stay in the same place, that is also a measurement, or we move to higher probability. So that means that in this specific case, we have AJ going to A to I, and AI going to J is larger or equal than 1. That's the only thing we know. Then we have the other situation where WXI of WXJ is smaller than 1. And in that case, we have AJ goes to I is less than 1. Now, I'm going to give you a hint, because this is what Metropolis and company used in order to find the algorithm. The only thing we know about the acceptance probabilities is that they are probabilities and they are normalized. So that means that these quantities, either going from J to I or I to J, have to be equal or less than 1. So if you now think of going to a higher probability, what could be a natural choice for this quantity J to I? Because the thing we know is that A, from moving from J to I, is larger than that one, right? That's the only thing we know. Then we know that the largest value is 1. So what could be a natural choice for the value of this one? This is actually what Metropolis and company did. What could be a choice for this value, AJ to I, knowing that it's larger than the one you have in the denominator, and that its largest value is just 1. You just put it to 1. Because then this one will be smaller than 1. If you put it to the max value, then you know that this one has to be smaller, so you put it to 1. You could have put it to other values, and people have played around with other values, but this has actually been shown to be the most efficient way of setting it up. So that means that if you do that, in this specific case here, no, sorry, not this one, but I was meaning actually that one. Sorry, I was looking at it. So in this specific case, you just put that one to 1. In the other case, it's actually reversed. So when it's less than 1, then we know that this one has to be larger than the numerator. And then you put this one to 1, and this one to be smaller than 1. And that's the essence of the Metropolis algorithm. So if you do that, if you use this kind of reasoning, so the max value, so when the probability A of J of AI goes to J is larger or equal to 1, then you take the max value. So then you say that AJ to I is just equal to the largest value. And in the other case, you have AJ goes to I. And in that case, we know that it's actually this one. And this is smaller than 1. Then we just put this one to 1. And that leads to the following, that A of J goes to I is equal to the minimization of 1 and the ratio between the probabilities. That's the acceptance probability. So what you would do then, when this one is Wi, Wj is smaller than 1, you would select a random number between 0 and 1, and you would simply compare that random number which you pick from a uniform distribution between 0 and 1, you would simply compare that to this ratio here. That's a Metropolis algorithm in its simplicity. And that's why it's so popular, because it's very simple to implement. It functions, it fulfills basically all the requirements we want, and it's very intuitive. So this is the way by which we can simulate the acceptance of new positions. So what I wanted to end with now is actually a calculation of a system which is pretty close to what we are going to do in the project. And I'm going to show you how you would implement these different items from a calculation point of view. So let's go back to the Jupyter notebook. And there is an example at the end here where so there are some mathematical interpretations about the Metropolis algorithm and the Markov chain. You can look them up here if you want to. I'm not going to go through them, but I'm going to look at the system now, which is similar to what you have in the project. So we have a non-interacting piece, which is the harmonic oscillator. And when we transform everything to relative coordinates, we can actually separate these degrees of freedom. So we would have an equation here, which you can solve analytically in 2 and 3 dimensions. So the harmonic oscillator potential problem with a Coulomb interaction has been solved analytically by Michael Taut in 2 and 3 dimensions. And what we are going to do now is to have a trial wave function, and I will come back to some of these discussions. And I will tell you why we have this specific form. This is something I will discuss in more detail next week, but now I simply wanted to show you the code which we can set up. So here I'm having a trial wave function which has a little bit more than harmonic oscillator. So this has also a part which contains correlations, but this first part here, this one which you see, no, not this one, but this part here is the position of particle 1 and particle 2 squared. And the wave function which you would need then, if you take away this deno, which includes correlations between the particles, for the plane harmonic oscillator you need in the project, you simply have this as a trial wave function. Then there is an analytical part of the local energy, where the thing you would need is just this part. This other part comes from the derivative of this uglier term, which goes like this. So this is a correlation part, which we will come back to how you can construct. But now we can just focus on the product of 2 harmonic oscillator wave functions and no interactions between the particles. But here I'm doing everything. So in this case, this is my local energy, which has an analytical expression. You can calculate the kinetic energy numerically, but that is going to require many more CPU cycles, because then you need to calculate the function at 3 different points since you're calculating a second derivative. So if you can calculate an analytical expression for the kinetic energy, either with paper and pencil, or you can use automatic differentiation, this is what you should do. That saves up to 75% of the CPU cycles, because you would else have to calculate a second derivative, which is the kinetic energy. And that is time consuming. Then, after we've done this, we have defined the wave function and the local energy. Here comes the Monte Carlo calculation in 3 dimensions. So I have the positions, I define the number of particles, the dimensions. So you can do this in 1, 2, or 3 dimensions if you want. Then I start with a variational parameter because I have the minimum at 1 if it doesn't interact. So I start with 0.9. So I define a set of variational parameters. And then I also know that this parameter beta, which I have, so this is actually the full case with interaction. This parameter beta, or this alpha 2 here, which I call beta in the program. This is a parameter which, where a good value to start with is 0.2. Then I calculate now the old position and the old wave function. This is the initialization. And now I have my loop of Monte Carlo cycles. I propose a new position where I simply use a uniform distribution. This is inefficient. Next week, when we discuss importance sampling, we will see how we can improve upon this kind of jumping in space according to a uniform distribution multiplied with a constant called step size, which we need to tune. So I'm running the calculations in Cartesian coordinates. You see X, Y, and Z, because this number random goes between 0 and 1. So subtracting 0.5 gives me negative and positive numbers. Then I set up the new wave function with a new position. And then I use my Metropolis test because I don't need a wave function normalization constant. And I just take the wave function u squared and the old squared. The way I have done it here is not very smart. So this is a very brute force way. And we are coming back to ways we can change this. Because here, I'm moving all particles at a time. You can save CPU cycles if you move one particle at a time, because then you will just have the ratio. If you look at this trial wave function, you will just have the ratio between particle 1, which is being moved. Particle 2 stays in the same position. So then I would just look at the ratio between what happens with particle 1 in the previous stage and in the next stage. So the way I did it here is not the most computational efficient way because I'm moving all particles. In many cases, what you will see, it's more convenient to move one particle at a time. Because then in the ratios, you don't need to call the full wave function. And as I said, to calculate the full probability for 10 particles is time consuming. Because we are sampling in 10 particles in 3 dimensions, that would be a 30-dimensional animal. This is only 6-dimensional. But I'm calculating a 6-dimensional object, and if I do this 1 million times, I'm doing that 1 million times. So that requires a lot of cycles. And also, there are more things you can simplify because you have exponentials here. So you don't need to calculate an exponential in the denominator and the numerator. You can simplify that operation so that you only calculate one exponential. So these are things which are worth thinking of. So when you see many of these codes, I'm warning you that I set them up the way I write the mathematics, but that is often not the smartest way of implementing it. Just keep that in mind. So these codes have a very, how to say, a pedagogical aspect in the sense that I try to link them with the equations. But that's often not the smartest way of doing it. So if we run through them, we have the Metropolis test here. If it's smaller than a random number, this is also not the smartest way because I could simply have asked if this is larger or equal than 1, I don't need to call a random number and have an if test. So there are many such small things which can be improved upon. And then when I've done that, I update the local energy. I add this to the energy and I calculate the energy squared. And then I can now run it. I have 2 particles. I set it in 2 dimensions. I can do 3 dimensions. I do 10 variations. In alpha and beta, I have 2 parameters. So that means that this produces a 10 by 10 matrix in the unknown, variational parameters. And if I run this, you will see that it takes some time, even with these few Monte Carlo cycles which I had, which in this case was set to just 10,000. And what you will see then is that the results, you see that there may be a minimum. Actually, the exact values is 3.0. So you have an analytical result here. But you will see that this landscape is a little bit rugged. So if I were to let this If I increase this to, let's say, 1 million, we can redo that. And then it's going to take more time. So we will need at least some 10 minutes on this slow Python code here. But the results will look much better. So the more Monte Carlo cycles, the happier we are. Oh, I have to restart everything. Sorry. Let's just restart. Yeah. Yeah. So let's take a break now, and we have the lab afterwards. And then we are going to continue these discussions about the different templates we have, and also how to implement the simplest Metropolis algorithm. And we are going to do that with just one particle in one dimension, 2 and 3. We have the analytical results, no interaction. And then we ramp it up with 2, 3, 10, 100, and so on, with no interactions. So if the code is going correct, running correctly, and giving us the exact result, then later we will bake in the interaction, which gives us the interest in physics. So this is going to take a little bit of time. So we get a quick answer when we had only 10,000 Monte Carlo cycles, but the results are not very impressive. You have large variations. You have large errors. And when you increase it, you will see that the results become better and better. This is also one of the reasons why writing a program in C++, which is normally a faster language than Python, is beneficial. So Python calculations until recently, before we got improvements with JAX and so on, tend to be much slower than what you would have in a low-level language like C++. I'm going to stop the recording now. I went a little bit over time, but I wanted to conclude with this. And next week, we will start looking at how we can improve the simple Metropolis jumping with what's called importance sampling.